My name is 𝗦𝗧𝗕𝗦𝗬𝗓. I am the process optimization specialist for Lakeside Process Control. And this is the 6th episode of a 10-episode series of webinars on process control, and we'll be talking about characterizing the output. So once again, there's guidelines. Your microphones are off, as was mine before. You can ask questions via the Q&A box on your screen. You can ask your questions anytime you want, but I will answer your questions at the end. There will be a Q&A session at the end, so I will answer them then. So I will read your question and then answer it. Now, you have to understand there is a 10-second time delay from the moment I speak to the moment you hear my voice. So if light travels at 300,000 kilometers a second, that means I'm over 3 million kilometers away from you. This is actually where I'm broadcasting from. So I challenge anyone to they could tell me what 1970s sci-fi episode or series this was from. Your questions are anonymous, so only I can see your questions. So don't be shy. I encourage questions. And if we run out of time, and I will try to make sure that we don't, but if we do run out of time, or if you think of a questions afterwards, you can always feel free to reach out to me at 𝗦𝗓𝗦𝗓𝗏@lakesidecontrols.com or on my cell phone, as you see here. You can go through the main number, but just probably contact me on my cell phone. And as I said, this is a series of 10 webinars, usually towards the end of the month. I did have a bit of a hiatus over the summer. And so this is a 6th one. Next one will be kind of similar to this one. We'll talk about adaptive control, talk about feed-forward control, split range, and dead time compensators. This is being recorded, so we will send you a link, or if you want to, I believe we will send you a link if you request it for the recording of this webinar. A bit of a safety moment here. This is actually very relevant to myself and actually to this week here for the hot weather. Dehydration and heat exhaustion. My friend and I built, we have a trailer, my wife and I, on Prince Edward County, a place called Whalers Bay, beautiful area. And my friend and I built a 12x12 deck. It was just over a week last Friday. Very, very super hot. 9 o'clock in the morning was already 25 degrees, very, very humid. And throughout the day, we built the deck in about 4 hours. But through that, I actually managed to get the heat exhaustion and sun heat stroke. And it took me over almost 2.5 days to actually recover. So it's always important to be proactive. By the time you actually kind of feel the effects of sunstroke or heat exhaustion, it's already it's too late. So to be proactive and also take it easy. There's no shame in just taking a break and so forth. Obviously, push myself too hard. So obviously, drink water. If you do get dehydrated, from what I've read, I'm not a doctor, but is better to sip some water continuously as opposed to chugging a whole glass of water. Let's talk about Lakeside a little bit. So we have our 325, and Lakeside is an employee-owned company from founded in 1952. We work in all the areas here from all those industries. I actually worked in pretty much every one of those industries. We are the exclusive Emerson rep for our area, and we're part of a network called the Emerson Impact Network. You can see here number 9, we are Lakeside, and our territory goes to a part of Nunavut, Manitoba, and Ontario, all the way to just this side of the Kingston border. So if it's east of Kingston, it becomes part of our friends at Laurentide Controls, but west is actually ours. And you can see there are over 21 Emerson Impact partners. And why do we have such a network is because we believe that we will better service our customers having a local presence as opposed to a monolithic corporate presence. So we're locally certified. We can actually service you better. And at the same time, we're the main point of contact between Emerson and yourself as well. We know who to call based on your inquiries. As you can see here, I never really liked this slide, but we do sell a lot of stuff from measurements, valves, regulator, control systems, and so forth. We also offer consulting services, training services as well. And we also have do some fabrication here in Mississauga as well as other sites as well. Our idea here is to provide a good, positive customer experience. We're really focused on customer experience, or CX as we call it. And I believe in our emails that you receive from us, there is a survey. We encourage you to provide us with feedback, whatever it is, good or bad feedback. There's actually no such thing as bad feedback. We need to hear from you. A little bit about myself. I have actually over 33 years experience in the field of optimization. I offer control optimization, loop tuning services. I go to site and do some troubleshooting and actually provide tuning services and troubleshooting. I'm also responsible for advanced controls and neural net applications. DCS alarm metrics. Anybody look at your DCS alarm banner? A lot of times, if you walk into a control room, typically it's full of alarms. A lot of them are maybe unacknowledged. Some of them are irrelevant. So the services we offer is that we actually do an alarm analysis. We could do a download of your alarms for a period, let's say 30 days, be able to go through and establish which ones are nuisance alarms, and we work our way from there. And from there, the idea is not to eliminate alarms. The objective is to make the alarms relevant to the operator. Any major industrial disaster that has occurred will have roots in poor alarm management. And that picture you see there is not a Google picture. It's actually a real picture we took at the controls at a customer site. This is during a shutdown. They didn't want the alarm to come on all the time, so they put a steak knife in there. Now, I do have two gentlemen that kind of help me out. They don't work for me. They work with me. As a matter of fact, actually, I think Andrew is my supervisor, believe it or not. So, and they provide me help whenever I need to. Dean is also a good resource to be able to help me out. And I do offer courses as well, basic instrumentation for operations. It's a 6-hour course, covers the basics of operation of instrumentation to get a good understanding how instrumentation, the common measurement, pressure, temperature, level, and flow, the different technologies, how do they work, how to troubleshoot them. I also have a course, Process Control Techniques 1, aka loop tuning, and obviously loop tuning 2 as well. So we talk about lambda tuning and so forth. I also have a blog, talk about different things. You can go to our website, just search for blog, and you'll come across these. The second one there, the unusual suspects. Actually, I'll be referring to that a little bit at the end of this webinar, about talking about gain scheduling, or actually output characterization. Okay, so here's the good stuff. So what are we going to cover? We're going to cover linear versus nonlinear. When and why should we or do we implement an output characterizer? Identify and characterize. So we decide to do it. How do we actually go ahead and do it? And I'll have a live demonstration showing you how this is actually going to be done, and then implementing, and so implementing the output characterizer. So linear versus nonlinear. So a linear process is a process that doesn't vary, depending, no matter where you're operating within your operating range, the process will behave exactly the same way. The process sensitivity will be the same. The process, if I get my pen going, the process sensitivity will be the same, meaning the change in output here. So here's the blue line is the output signal to the final control element. The yellow line is a measurement feedback. And you can see here, no matter where I do my bumps, the process actually responds exactly the same. Whereas here, you can see I open up make a equal command signal changes increasingly. And you can see here, I get a large change. In this case, is a flow. but the more I open my valve, the less and less flow change do I see. And this example here, we'll call this a quick opening flow characteristic. And what can actually cause that? Traditional butterfly valves are known to have a quick opening flow characteristic. As a matter of fact, a butterfly valve, there's some people in my crowd here may argue with me, but usually between 60 to 65% open or more, you're no longer controlling. You're actually in this area over here. You're no longer controlling. And at the bottom end, very, very sensitive. Another one is actually be the focus of our the focus of this webinar is on air dampers as well, especially on boilers. Now, let's face it, linear processes do not exist. We all, every single process will have some mild non-linearities. And if you can tune it in a robust way, knowing that your process will change depending on the operating conditions, you can tune in such a way that it can withstand and remain stable under those mild non-linearities. But there are cases, as we just saw, that if the process is highly nonlinear, then we need to implement a different strategy. And why do we do this? So right here, you can see here again that so the white line you see there is the set point change. So the controller is in automatic mode. The yellow line is the measurement, and then the blue line is the command signal to the final control element. And so if I tune it here at the upper end, because as I just showed you before, the more and more closed the valve is, the more sensitive the process becomes, that your tuning changes. And therefore, as it closes with the same tuning, it becomes less sensitive. Here's another example here. This is more of a pH application, pH control, where especially if it's a strong acid, strong base dilution or neutralization, is that I can tune it here at the buffer region and remain stable. But as you remember, the titration for a strong acid, strong base is like this. The process becomes very sensitive around a pH of 7. And so therefore, once again, knowing how the process changes, we need to understand that will actually force us to actually consider a different control strategy. Okay, so the steps. How do we actually implement? So first of all, we got to decide, is this required? Does the process change enough? Do we need a good, a wide operating range? Is an output characterizer required? Let's face it, I've spent a lot of my time through my career to try to simplify things as much as I can. And therefore, we have to consider, is this required? If it is required, then we need to identify the key variable. What variable out there is going to show us or give us an indication of that particular process nonlinearity? Could be a pH value, as I just showed you before, or could be the damper output or output to a control valve like a butterfly valve. So today we're going to key on the damper output. In fact, the pH value, we would use a different strategy, an adaptive tuning strategy, which is the subject of my next webinar in September. So here we're going to key in on the damper value. We need to quantify the nonlinearity. We need to understand that nonlinearity, because once we know that, then we will be able to undo it. We do that by collecting data, XY plots, graph, and we'll do a regression analysis. Once we understand that, then we'll be able to undo that nonlinearity, essentially we're going to linearize that nonlinearity, and that will make our job a lot easier. So how do we do that? Again, back to this forced draft FD airflow control. So you can see here, we did some bump tests, and here we determined that, yes, it is very nonlinear, quick opening. And we're going to implement a characterizer right here in order to linearize the relationship between the output here and the flow over here. And that is the objective. Another way of looking at it is like this. We got our flow measurement here, their flow measurement coming into the PID block. The PID block, the output of the PID block goes into the characterizer block, which we need to develop. And then the output of that characterizer block goes to the analog output and to the damper actuator. Now, another thing that's important here is that if we do this, and I've done this a few times, is that it's important on the graphic display for the operator that the operator needs not only to see the output of the PID, but the actual output to the final control element. In this example here, you can see 40% PID output right there yields a PID output of 18%. This is the operator needs to know where the actual output is, or the actual final actuator is. So it's very, very important that you put both those values there. So therefore the operator will know exactly where that valve position is. So we're going to do an example here. And then, so here we go. So you've seen this graph before, this chart before. And so FD fan control. So controlling the forced draft flow control is typically ratioed to the fuel flow, let's say natural gas. And obviously we want to keep a constant ratio to get maximum combustion efficiency. If we put too much air, then we actually could be cooling down the flame going out, increasing the percent O2 coming out of the stack. We're losing energy. And if we don't put enough air, we might get incomplete combustion, increased carbon monoxide output, and a potential for an explosion. So what I did here for time's sake, all right, it's not cooperating with me. All right, so let's go over here. So I will actually show you, I'll make step changes. As a matter of fact, maybe I could look at it this way here. I just want to save a bit of time here. There we go. There we go. Okay. So what we have here, again, I showed you this chart before, where the blue line is command output to the final control element, the air damper, and the yellow line is the flow signal. And I did equal amount of changes, so these are all 10% changes, and you can definitely recognize the fact that this is a quick opening flow characteristic. So what I'm going to do is that I developed a spreadsheet here that will actually plot that nonlinear flow characteristic, and we'll do a regression analysis, and then from there we will develop our output characterizer. So the way I do that is that I will then at 10%, I will record what the flow is at 10%. So here is 22,337. So here I'm going to say 22,337. This chart right here, flow versus output, is plotting these values here and these values here. So let's go over here at 20%, 40102. So let's say 40102, and it automatically starts to plot it. Let's go over here at 30%. 𝗫𝗫𝗡𝗙𝗫𝗓𝗏. 𝗫𝗫𝗡𝗙𝗢𝗏. So as I'm typing it in, you can see the chart here is updating, and you see my regression equation is actually updating as well. Let's go to 40%. 65195. All right, 65195. Once again, that's updating. 71788 at 50%. 71788 at 50%. Let's go to 60%. 76934. 76934. At 70%, 80035. 80035. At 80%, 82223. 82223. And at 90%, 83199. 83199. So, okay, so let's take a look at this. So you can see here, we definitely have our quick opening flow characteristics. I put in all those points. I got my regression equation. It's a cubic equation. Very good R squared, almost one, almost a perfect fit. The graph below, it shows you the process gain or process sensitivity as the valve opens up. It's essentially the slope between each of these points. And you can see here, initially at 10%, the actual process gain is 1.78. And around 90%, it's 0.1. That's over a 10 times less sensitive at the top end than it is at the beginning, at the opening end. So you can see here, obviously, this is a highly nonlinear process, and we do need to implement an output characterizer there. So the next step here is this chart right here. So that chart is what I'm doing is that I'm going to, this is the valve position, this is the PID output. So what I'm going to do now is that I'm going to adjust the valve position. Actually, the first thing I'm going to do is input those parameters right here, the coefficients. So that is going to be 0.0962. That's the coefficient for the x cube, minus 26.427 for the x squared, 2523.6, that's for the x, and 0 for the constant. So now, using this equation right here, I can calculate based on the valve position what that flow will be. So you can see here it's actually 22,690, whereas 22,000, we're very, very close. So this is where we're going to implement or design our characterizer. What I'm going to do is that I'm going to change these values and look at this plot and try to linearize, and we will linearize that flow response. The chart below shows you the relationship between the output of the PID, so this column here, and this column here. So the bottom is the output of the PID block. The Y column is the valve position, and that will be our characterizer. So you can play, usually you play around with this a little bit. I've already got the answers here for time's sake. So for a 10% output, the valve will be at 5%. For a 20% output, the valve will be at 9%. And you can see here, that chart is updating. The next one for a 30% output will be 13% valve. For a 40, it's going to be 18%. For a 50, will be 25%. For 60, will be 33%. For 70, be 45%. For 80, 63%. And 90 is 90. So you could see here that relationship now is linear. But to get that linear relationship, the output must go through this characterizer block in order to achieve that linear relationship. Now, if you take a look at this chart here and this chart here, they're kind of a mirror image of each other, which does make sense. So what we're doing here, as we're approaching the top end here, we're going to be losing some of that modulation capabilities. This is where we get the extra kick. Okay, so now what I'm going to do is going to implement that into my configuration. So right here, this is the current characterizer. It's just a 1-to-1 right now. So what I'm going to do, and one thing I want you to pay attention to, I'm going to put this back to 10% for now, is that the output here is the output of the TID block. Down here is the actual position of the damper. So once again, I'm going to change this value here. Go 5. Go 9. 13. 18. 25. 33. No, not that one. Next one. 45. 63. And 90. So you can see here, it actually plotted that curve, which is very similar to this curve here. A couple more things I want to talk to you about here also is that now by implementing this characterizer, we've actually created a new process, and the slope of that linear line is the actual process gain. So I'm going to do that. I'm going to calculate then one set of tuning parameters that's going to operate well at all ranges. So I'm going to put that slope inside here. That's this spreadsheet automatically will calculate the tuning parameters for me. So it tells me, based on the slope, that my gain should be 0.36 and my integral is 5 seconds. So I'm going to implement that right here. So I got to change the tuning. 0.36 and 5 seconds already. Okay. I'm going to put this down to 10. I'll put it at 15,000. I'm going to put the chart back up here. Go back to here. As a matter of fact, we'll go to this one. So in this chart, it's a little bit different. The yellow, again, is the flow signal. The white is the set point. The blue line is the command signal from the PID block. And the orange line is the actual damper position. So since now I've implemented the characterizer, the output is at 10%, but the damper is actually at 5%. So I put this in automatic mode. So before I do that, I'll actually go back to this chart here. And I'll show you some set point changes I made without the characterizer. And I had tuned it up at the upper end where the process is less sensitive. And I made equal set point changes down. And you could see that it becomes less and less stable. Let's go back to here. Okay. So now I put it in automatic mode. And now I can make a substantial set point change, let's say to 45,000. And you can see here the valve, it does not match the output, but the controls will remain stable. So as you go along, so obviously, and then if I make another set point change, so I'll just wait this to reach set point or near set point. You can see the output, the valve position changed by this much. If I change this to 65,000, the actual damper will actually start to move more because we are at the upper end. We're starting into the upper end of the characterizer where for equal amount of changes and the PID output, I will get more and more damper change. And you can see that happening right there. Matter of fact, I probably got to go up to 75,000. And that's a bit different from what we had before, because before we could tune it at one end. That would be, go back to over here. Go back to here. Here I tuned it at the upper end and was getting less and less stable at the bottom end because the process sensitivity was increasing. Or I could have tuned it down here to be stable at the bottom end, but the response would have been very, very slow at the top end. So this is why implementing a characterizer gives us a identical response no matter where we operate in our output. So I'm going to share with you another story about where I actually implemented a character. I've actually implemented a couple of places. In this example here, this is a large boiler and 300 tons an hour. And it turns out in this example here that the valve was not the problem. It was actually the feed water pump was wearing out and could not supply enough pressure at the upper end, could not control. So what you're seeing there is actual data. Here at the bottom end is actually tons per hour, and this is pressure. So this is pressure, and this is flow. And you can see, it's difficult to see, but the actual pressure would drop from 267 tons an hour down to 300, almost 38 tons an hour. It would drop by almost 1,500 kPAs, which is significant. And so I actually did an XY curve. And what I want you to do is pay attention here. This is valve output, flow rate. And so what you see here, this is back in December of 2018. I collected the same data in April of 2019, and you can definitely see the pump is starting to, this is my technical term, is starting to wilt. And then this is in May of 2019, and you can definitely see a very nonlinear flow characteristic. And so obviously we know with the boiler feed water, we have a feed water flow controller. We could tune it down here, but the response, if it's operating up here, which is where they operate a lot of the times, would be very slow. And therefore that would cause a drum level swing. Again, I could tune it up here, but at low loads, it would be unstable. And so therefore I had to implement a characterizer, not because the valve was actually nonlinear, because the pump itself was actually unable to supply a flow to supply the flow at the top end. Just like I showed you before, I developed a regression and use a cubic equation, and that's the cubic equation, which then I use to calculate to linearize the flow characteristic. And once again, you could see here, that is the characterizer. So they're, just as I showed you before, 0 to 100%, I had to change these values to linearize the flow, which then established the characterizer, which is at the bottom side here. Based on that, it gives us a linear flow characteristics. And the actual data here, this is the actual data. This is all on the same scale. And so before the top end, you could see it was tapping out at the top. Using the characterizer, it was actually achieved a pretty good linear relationship. So that's it for now. Q&A is coming up. Once again, September 15th, changes with the time. I'll be talking about adaptive tuning, another way of actually doing this. We'll be using a pH example as our example. So I hope to see you there. And I'm now going to open it up for Q&A. And I know there is a 10-second time delay, so I will wait 10 seconds. And I encourage you to ask questions. So I'm still waiting for questions. Awesome, I got a question here. So sorry I joined a few minutes late. Are you going to share these slides or presentation? Yes, as I mentioned, this session is being recorded. And should you wish to we can send you a link. I think it takes a few hours to generate the through a platform, generate the video. But yes, we can share this recording with you. There must be more questions out there. Awesome. Okay. Please use a bigger cursor pointer for us to follow. Okay. Point well taken. Thank you very much for the feedback. I appreciate that. So far, so good. Just wait. I'm sure there must be more questions than that. Okay, I'll give it another minute or so. All right, I'm still waiting for questions. As I mentioned, if you think of questions after this webinar, you're more than welcome to contact me. All right. Just got to wait a little bit longer. I want to make sure that capture any kind of questions. Okay, well, thank you very much all for attending. Certainly really appreciate you attending, and I hope to see you at my next webinar, September 15th, on adaptive tuning. And like I said, if you do think of questions afterwards, we can certainly, I will certainly be able to just contact me, and I'll be able to email you, and we'll answer your questions then. Thank you very much for your time. Stay safe, stay hydrated, stay cool, stay healthy. Thank you very much. Enjoy the rest of your day. Thank you.